In this video, we are going to do some exercise problems from Chapter 2. The steel framework is used to support the reinforced stone concrete slab that is being used for an office. The slab is 200 millimeter thick. Sketch the loadings acting on the member BE and FED. To solve this problem, first of all, we need to determine whether it's a one-way or two-way slab system. So let's get our ratio, which is length of the beam divided by span. This comes up to 2.5, which is greater than 2, therefore it's a one-way slab system. Now, you know that this is stone concrete slab. Stone concrete in our table 1.2 minimum densities for design loads is 22.6. Solving for member BE, get the dead load, 22.6 kilonewton meter cube. Slab is 0.2 meter thick times the area of the slab that will be handled by the beam BE. In this case, it's 2. All of this is equal to 9.04 kilonewton per meter. Now the live load is, it's a office building, so for offices, live load, or at least the minimum live load, is 2.4 kilonewton per meter square. Area, or the width of the slab that will be handled by our beam BE is 2 meters, and solving this we get 4.8 kilonewton per meter. Adding both these together to get the total load, and it's 13.84 kilonewton per meter. The idealized beam BE will have a uniform distributed load as follows. It will be 13.84 kilonewton per meter. Now we need to convert this load into a point load, which is simply multiplying our total load with the length of the beam. In this case, it's 5 meters. Point load is 69.2. Let's find our point load for BE. And that'll be simply, because there isn't any other force acting on this beam at this moment, it'll be simply 69.2 divided by 2, and this comes up to 34.6 for each of the point. Now let's solve for the loading on the member FED. So for FED, we know, let's draw the free body diagram, FE and D. We have already found the loading for point E, which is going to be 34.6 kilonewton. And we know that the beam AF and CD will have half the loading of whatever our member FBE had. Therefore, simply dividing 34 by 2, we'll get the loading for point D and F, which is 17.3. All right, and there we have it, our answer, our solution for this problem. Okay, now what if our span is 3 meters now, and our length of the beam is 4 meters? Okay. Now, first of all, we need to determine whether it's a one-way system or a two-way slab system. To get that, we need to do our ratio once again. So 4 divided by 3 is 1.33, which is less than 2. Therefore, it's a two-way slab system. To solve for a two-way slab system, first of all, let's draw our idealized framing plan, and we have a beam in the center, BE. Now for 2A, we know from our theory lecture that the forces are divided at 45-degree angle at the corners, go into the center, and then the middle part has a loading, normal uniform loading, as we have in a one-way slab system. Okay, so first of all, to solve this problem, we need to determine these points here where our triangular load starts being a uniform load again. Okay, so we know our length is 4 meters and this length or our width is 3 meters. We can use tan 45 to determine our point A here. So we know that this center line is halfway through the length of EF. So therefore it will be 1.5 divided by A. Solving for A, we get 1.5 meter as our length for our A. And we know, because this is a symmetrical structure, our value for B will also be 1.5 meters. Okay, now let's find our dead load, which is pretty similar to what we did in the first example. So 22.6 kilonewton meter cube times 0.2 meters for our slab thickness times the span, which is 3 in this case. Solving this, we have 13.56 kilonewton per meter, and our live load is same as before, 2.4 kilonewton meter square times 3 meters, which is 7.2 kilonewton per meter. Adding both of these together, we get 20.76 kilonewton per meter. Now let's draw our idealized free body diagram for BE. So our loading for BE will be trapezoidal, and it's not to scale. So our maximum top load for BE will be 26.7 kilonewton per meter, and these are 1.5. The whole length is 4 meters, and this middle point here is 1 meter. Okay, now we can find our point load, which will be here in the center, first of all. Okay, to do that, we have to do our point load. Okay, let's do our point load in red. It will be 2 times area of the triangle, 0.5 times 1.5 times 20.76, plus the area of rectangle, which is 20.76 times 1 meter. Solving this, we have our answer as 51.9, and now dividing this by 2, we should get our value for each point B and E. Load comes up to 25.95 kilonewton. On each side. Now we can calculate our values for our point loads. Well, before finding point load, we need to find our values for idealized girder. And our uniform load for girder will be as follows. So we have a point F, E, and D. And we know that our E is 3 meters away from F, and it's another 3 meters away from D. So 3 on each side. And our point load, sorry, our distributed load is going to look something like this in a triangular form. To calculate our total load, we need to calculate our dead load, which is 22.6 times the thickness of our beam times, let's calculate the dead load, which is going to be 22.6 kilonewton meter cube times cube thickness times half the distance of the span between F and E. Solving this, you got 6.8 kilonewton meter, and then our live load, just 2.4 kilonewton meter cube times 0.2 for our thickness. Oh, never mind, we don't need a thickness for our live load. We just simply need the length of the load that will be handled by the section FE, and which is 1.5. Following this, we get 3.6. Adding both these values together to get our total load, and it is 10.38. Another way to get this peak load on the girder is simply dividing the peak load of our middle beam by 2, and we get the same value as we get by solving for dead load and live load. Okay, now that we have those, we can calculate our point loads. So we already have one point load for member BE. So point load E has 25.95 kilonewton extra from the member BE. And then we have to calculate this load that will be carried by point E as well. So this would be simply 2 times the area of the triangle. For this case, it's half 0.5 times 10.38. We get 15.57. So we have another 15.57 here that will be handled by point E. And now we can simply get the area of the triangle for point F and D, and we get the value 7.79 for both of these points. We also have to remember here that load from the joist needs to be added into our point load at D and E. So that's going to be pretty much 25.95 divided by 2 gives us 12.975. So it'll be 12.975 plus 7.79 as our point for point F and D.